Okay, the name of the game is Free Body Diagrams and Newton's Second Law. In this video I want to work through multiple problems, drawing free body diagrams, identifying all the forces on something, and then using that to find the net force, and then plugging that net force into Newton's second law, obtaining the acceleration of the object. Occasionally we work backwards. My hand. Starting with the acceleration and figuring out what forces are needed to create that acceleration. So we can work given F find A or given A find F. The two are related according to this very famous equation. The sum of forces on an object divided by the object's mass equals the object's acceleration. This is a mathematical form of Newton's second law, relating three variables. So let's proceed. We have a guy pushing a giant box that is 45 kilograms in mass. We see the box moving right at constant speed. The fact that we witness it moving at a constant speed, not accelerating, tells us that the forces on the box must be balanced. The forces on the box must be balanced. Unbalanced forces cause acceleration. Balanced forces cause no change in motion. The constant speed indicates that the object is not accelerating. The man is pushing with a force of 50 newtons. This problem is pretty easy. Let's start by writing down a couple of things. First, for all these problems, we're going to analyze them in terms of horizontal motion and vertical motion separately. Okay? So we will decide, is the object accelerating horizontally, that is left or right, and separately, is it accelerating vertically, up or down? Okay? In this case, the answer to both questions is no. The acceleration in the horizontal or x direction is 0, as is the acceleration in the y direction. Okay? Based on this equation right here, Newton's second law, this tells us that the forces in the x direction must sum to 0. The notation means the sum of all the forces in the x direction, that is, any force right minus any force left, has to add to 0. We have an applied force to the right. The guy is pushing right. We would have some friction opposite that direction, and the applied force minus the friction would have to equal 0. Because the man is pushing with a force of 50, the applied force is 50. Therefore, friction must also be 50. If we were to draw a free body diagram, we would show 50 newtons applied force that way, and 50 newtons applied friction force that way. They should be the same length. I didn't draw them very carefully. Let's recreate the same steps for the vertical component. We see that the box is not accelerating up or down. We witness the box sliding constantly to the right. This tells us that the sum of the forces in the y direction must be 0. Any force up minus any force down must equal 0. In this case, there are two forces vertically. There is the normal force up and gravity down. The normal force minus gravity equals 0. Okay. The force of gravity for something that is 45 kilograms is approximately 450 newtons. More specifically, it is 45 times 9.8. But I'm just going to say approximately 450 newtons. If that's Fg, then Fn must also be 450 newtons. in order to balance. Okay, so here's our free body diagram. We have our four forces. This one is Fg, this one is Fn, this one is FAPP for applied, and this one is FF for friction. There really wasn't a question, was there? There wasn't a question, so what we just did with the problem was we figured out what all the forces were. Okay, now we go to number 2. Here we see a box accelerating to the right. That tells us that the forces are not going to balance horizontally. But seeing as the box is not accelerating up or down, the two forces vertically do balance. Okay, if the man pushes with a force of 100 newtons and friction is 90 newtons, find the rate of acceleration. Again, let's start by writing down AX, that is the acceleration in the x direction. Okay, we don't know that it's 0, so we're not going to set it equal to 0. In this case, we need to solve for what it is. So we do that using Newton's second law. The sum of the forces in the x direction divided by the mass will give us the acceleration. The sum of the forces is a 100 Newton force to the right minus a 90 Newton force to the left, divided by a mass, which is 45 kilograms. That equals 10 newtons over 45 kilograms, which comes out to 0.22 meters per second squared. So the object is accelerating to the right at 0.22 meters per second. We could draw a free body diagram here showing the force to the right, that is 100, the force to the left, which is slightly smaller, 90. To make this a complete diagram, we also need the vertical forces, that is, we need force of gravity and we need the corresponding normal force. While gravity and the normal force aren't always the same number, here they are, and a lot of times they are. Okay. These numbers are pretty easy to obtain. If I'm going to try to mimic the same format here, I would say AY equals 0. Therefore, the sum of the forces in the y direction equals 0. Therefore, the normal force minus gravity equals 0. Gravity is 450 again, therefore the normal force must also be 450. But our answer is this right here. The acceleration is a positive 0.22 meters per second squared. The direction is to the right. Number 3. Now we have a lady pushing a giant box, 30 kilograms. We see the box accelerating to the right. That tells us, or we're told, right? That tells us that the forces are unbalanced in the horizontal direction. We do not see, or we're not told, that the box is accelerating up or down. Therefore, we assume the forces are balanced vertically. Okay. So, if the rate of acceleration is 2.2 meters per second squared and a woman pushes with a force of 126 newtons, how much force must friction be? We'll start in the same way. AX equals 2.2 meters per second squared. We are told the A in this case, we don't have to solve for it. It's not 0. We are told that it's 2.2. This has to be the sum of the forces in the x direction divided by the mass of the object. The sum of the forces is the force applied by the woman, which is 126, minus the force of friction divided by the mass. That is 126 newtons minus F over 30. Okay. 2.2 equals 126 minus F over 30. Multiplying both sides by 30, rearranging to solve for the force of friction, we get, well, 66 kilogram meter per second squared equals 126 newtons minus force of friction. Force of friction must equal 60. And it's to the left. So on our free body diagram that we're going to draw, we'll have 60 to the left, 126 to the right. What about up and down? The forces balance. AY equals 0. By the same argument as above, the normal force must equal gravity. They will both be 300. So let's draw our free body diagram over here. We have down of 300 based on a mass of 30 kilograms, a normal force of 300, to the right of 126, and to the left of 60. Okay, let's move on. So, what this is representing is two people pulling a box using ropes, and this is a top view. Okay, so we're seeing the top of the box, and two different tension forces. Okay, if we were to draw the free body diagram for this, the diagram would need to be three-dimensional, because not only do we have forces in the XY plane, but we have them in the Z plane. That is, since this is a top view, the normal force goes straight up into the air, and the gravitational force goes straight down into the paper. We would need a Z-axis. Given that this is a box, and the implication, or maybe I tell you that we see it scooting along the ground, we know that it's not accelerating vertically, we know that the weight and the normal force balance. Let's leave them off the diagram because they're going to cancel out anyway, and cause I don't like to draw 3D. So this is a diagram showing just the two forces, 180 and 150, and I'm not going to draw the other two vectors because they are in the third dimension, one going down and one coming up off the page, and they would cancel anyway. Our goal for this problem is to find the acceleration of this box, and I can find the acceleration without using the Z dimension. So, moving forward as we've done in the past, this time X and Y represent well, Y doesn't represent moving up into the sky. In this case, X and Y represents basically a 2D plane, or positions on a 2D plane. Before we can progress, we need to take the 150 newtons and break it into its components. Okay. The AX and the AY we do not know in advance, right? It's not balanced. They're not zero. We're not told what these two forces are. Ultimately, we're going to need to figure out the sum of the force in the X direction, and we're going to need to find the sum of the force in the Y direction. Okay. In the X direction, we have 180, but we also have the X component of the 150. And so basically you would take the 150 and break it up into components. Okay. And this component right here, plus 180, equals our total fx, and just this component right here equals our total fy. We use trig to find these two sides because this makes basically a right triangle. If this angle right here is 20 degrees, then so is this one. That means that this side right here is 150 times cosine of 20, and this side right here is 150 times sine of 20. The total force in the x direction is 150 newtons times cosine of 20 degrees plus an additional 180 newtons. The total force in the y direction is 150 newtons times sine of 20 degrees. Okay, this is the strength of the overall pull right and the strength of the overall pull up. Let's actually calculate these. So this one should come out to 231.3 newtons, and this one should come out to, let me verify, oops, so this one comes out to actually 321, and this one comes out to 51.3. This is 321.0 and 51.3 newtons. Okay. And now we need to divide by the mass in order to get the acceleration. So all of this needs to be divided by the mass, which is 250 kilograms. And likewise over here, and we get the acceleration is, well, the components of the acceleration, 0.205 meters per second squared, and 1.284 meters per second squared. Okay. So this is the first problem that we've done where the y or the x didn't cancel out. We ended up with some overall force in both the x and the y direction, which meant we had some overall acceleration in the x and the y direction. In what direction does the box actually accelerate? Well, we have to add these together as vectors. That is, we have an acceleration to the right of 1.284 meters per second squared. We have an acceleration upward of 0.205 meters per second squared. And the overall acceleration, the acceleration that the box actually experiences, is the sum of these two. It is the resultant, which is equivalent to the hypotenuse of a right triangle. We use the Pythagorean theorem. and we get 1.30 meters per second squared. So the answer to the question, at what rate does this box accelerate based on these two forces? The answer is 1.30 meters per second squared at whatever angle that is. We can find the angle using inverse tangent. Looks like it's about 9 degrees. So the acceleration overall is 1.30 meters per second squared at 9.1 degrees. Okay, we're done with this problem. Okay. So, just to point something out, you could also have determined the overall force instead of finding the overall acceleration by saying the overall force in the x direction is 321 newtons and the overall force in the y direction is 51.3 newtons, and then determining the overall force right here, which would be what? Basically 325.1 newtons. And now with the overall force, that can get plugged into Newton's second law. That is the sum of the forces overall. I'm not going to put an x or a y on it. It's the total force divided by the mass equals the acceleration overall. That is 325.1 over a mass of 250 kilograms equals the answer we've already seen, 1.30 meters per second squared. So just know that you can sum the f's and then divide by m, or you can sum the a's. Okay, think about that for a bit and let us move on. How long is this video going to be? I hope not too long, but hope it's helpful. Here's another one. This one is simpler than the last one because here we have an object moving in one direction. It's moving up. There is no x component. It's only y. So we move back to the kind of problems we were doing earlier. And we don't have to use trig. So we see a bucket accelerating upwards at a rate of 0.6 meters per second squared. We want to find the upward force or the upward tension on the bucket. Okay. The acceleration in the x direction is 0. There are no forces in the x direction. Okay. But the acceleration in the y direction is 0.60 meters per second squared. And it is equal to the sum of the forces in the y direction divided by the mass of the object, with the sum being the force of tension minus the force of gravity. The tension force is what we're solving for. The force of gravity would be 50 newtons based on a mass of 5 kilograms, and the mass is the 5 kilograms. So 0.6 equals F minus 50 over 5. Multiply both sides by 5 and we get 3 equals Ft minus 50 newtons, or tension force must be 53 newtons. So the tension force must be greater than the weight, otherwise it would not accelerate up. It is 3 newtons greater than the weight, apparently. By the way, a kilogram meter per second squared is equivalent to a Newton. That's what a Newton is. Moving right along to number 5. This is a sign hanging from a building, advertising hatch. We see this sign at rest. We see that it's at rest. We see that it's not accelerating. Left, right, up, down. The forces must balance. We want to find the tension in these two ropes, what it has to be in order to balance the gravitational pull of 120 newtons. Hey, I didn't even do a free body diagram for the one above, did I? Did that upset you that I did not do that? Can I do it real quick? Gravity down 50, tension up 53. You feel better? Okay. So I come over here to this one. Let's draw a free body diagram. We can't put all the numbers on it yet, but we can draw a diagram. We can go ahead and put gravity. The force of gravity is 120 newtons approximately. Then there's a tension force kind of up at this steep angle, and there's a tension force this way. And these all have to balance. I'm going to call these by different names so that I can use them in a mathematical equation. Let's call this one T1 and call this one T2. Okay, and this is 60 degrees right here. The sum of the forces must balance. The object is not accelerating vertically, therefore the sum of the forces in the y direction must be 0. Okay, and divided by m, it's still 0. Okay, what are the forces in the y direction? Well, because we have this one at an angle, we need to break it up into its components. The upward component would be T2 times sine of 60 degrees. So we would say the sum of the upward or the vertical components is T2 sine of 60 degrees minus the force of gravity, which is 120 newtons, has to equal 0. So here's an equation we can solve, and we can find T2. And we're halfway done. Okay, so T2 would equal 120 newtons divided by sine of 60. Which equals 138.6 newtons. What about in the x direction? In the x direction we have AX equals 0. The sum of the forces in the x direction must be 0. Okay, and that tells us that T2 cosine 60 degrees, do you see what that refers to? Right here. T2 cosine 60 degrees minus T1 has to equal 0. That is, T1 equals T2 cosine 60. Which is 138.6 newtons times cosine of 60. Therefore, T1 must equal 69.3 newtons. So we have found our two tension forces, 69.3 and 138.6. And we could label them if we wanted to, here and here. Okay. Last problem. Maybe I'll just get you started on this one. It's probably like nearly time to turn this video off. Okay, I can no longer tell if this is lined up with the camera. So I hope I'm not off screen. Here, I don't know. Anyway, in this last problem, we have an object hanging from 2 ropes. We see a weight hanging from 2 cables. To find the tension on each cable, if we see it just hanging there, we see that it's not accelerating. We know all the forces balance. We know that all the vertical forces balance, and separately all the horizontal forces balance. Okay. Our free body diagram would look like this. Okay, there's 3 vectors, 3 forces. Maybe we call this T1, call this T2, call this gravity, which we know to be 400 newtons based on a mass of 40 kilograms. We break up our 2 tension vectors into components here and here, here and here. Okay, this one right here, T2 sine of this angle. And this one right here, T1 sine of this angle, have to sum to 400 because they have to balance 400. That is because the acceleration in the y direction is 0. Okay, and that equals the sum of the forces in the y direction divided by the mass. This delta, the sum of Fy has to be 0. Okay, this means that T1 sine of 40 plus T2 sine of 68 minus 400 equals 0. Equals 0, it already says equals 0, right? So up plus up minus down. Okay, so basically I'm trying to fit it into Newton's second law, but really it's just an equation on F. This is the equation right here. 0 equals T1 sine 40 plus T2 sine 68 minus 400. And we need one other equation. With 2 unknowns, we need 2 equations to solve. The other equation is a reference to x. It is the fact that the sum of the forces in the x direction must also equal 0, and they are T2 cosine 68 degrees minus T1 cosine of 40 degrees has to equal 0. Okay, on the drawing that would be labeled here T2 cosine of 68 and T1 cosine of 40. You should notice that if this is 68, then so is this. And if that's 40, then so is this. I think you cover that in geometry. Maybe these are 2 parallel lines crossed by a straight line. Anyway, it comes down to algebra and solving these 2 equations simultaneously. Again, I can't tell if I'm on the screen, so I hope I'm on the screen. What I would do at this point probably is solve this bottom one for like T1 and then substitute into the top equation. So T1 equals T2 cosine 68 degrees over cosine of 40 degrees. Take a second to see how that's true. Now substitute that in up above. You get 0 equals T2 cosine 68 times sine of 40 all over cosine of 40 plus T2 sine of 68 minus 400. Okay. Then you can factor out the T2. Let's add the 400 to the other side. So now we have 400 newtons equals. I'm going to factor a T2 out of these 2 terms. Okay? To get back to where we were before, you would distribute. So I did the opposite of distribution. I factored out the T2 from the two terms that had it. Okay? Now I basically calculate what this is in my calculator and divide it into 400. I guess I'll do it. Comes out to 1.24. So T2 must be 322.2 newtons. You can plug it back in right over here to get T1. And T1 comes out to 157.6 newtons. Okay, so we know the two tension forces. Okay, I hope this long video helped. Ciao.